Okay, for people who are joining this live stream, this is a discussion of a future feature for Wolfram Language, which actually I haven't seen for a very long time. So I'm excited to take a look at this. So I gather there's a slideshow here. Maybe I should bring up the slideshow.
Yeah, is it okay? This is a good slideshow. So
let's just go through it.
Okay, let's do that.
Okay. Okay.
So these are all...
Come on, Clio is extinct. I'm joking.
Okay. These are all examples that use microcontrollers of the kind that we support.
So which are the vendors, typically? Atmel, TI, things like that?
Yes.
Yes.
Who else?
STM. So there are microcontrollers, and there are also like board manufacturers. So Microchip, TI, these are all microcontroller manufacturers. And then there are people who build on top of that, like Adafruit, Pololu, and so on.
Yeah, okay. Right, but that's different from the market, you know, the Raspberry Pi, BeagleBone, etc. type market, where those are actual computers.
Yeah, exactly. Yeah. So these, yeah, microcontrollers, yeah, it's different because there's no operating system.
Yeah, I understand.
Yeah.
So what has been the trend of operating system-less devices?
Well, these date back a long time, but also today, when you build them, there are sort of two levels. So if you have a drone, the thing that actually controls the motors for the drone are the things that we're going to talk about today.
Okay, flight controllers as opposed to the main brain.
Right, as opposed to the macro level that orchestrates, that deals with network connectivity, that deals with sort of commands coming in.
Okay, so we're seeing a bunch of different...
The macro level thing runs at a very slow pace compared to these...
what are the typical clock frequencies of these things?
Oh, the 16 megahertz, 1 megahertz, and so on.
So they're very slow. So I'm confused here. So the point is they're running very simple code, even though their clock frequency is slow. I mean, because a typical clock for a microprocessor would be gigahertz.
Yeah. But this is on the metal signal processing, on the metal control. Those are very simple codes. They're real. They're hard real time. If something goes wrong there, it goes horribly wrong.
Yeah, right. So let me just understand, though. I mean, the trend, obviously, as soon as you're running neural net stuff, you're running much more general purpose. I mean, people are not trying to download that to Arduinos, are they?
No.
But what's happening, the neural network stuff is in terms of deployment in real-time systems, is getting... there's a ton of startups that are building hardware that are sort of special purpose hardware, and that's very much not general purpose controller computers. They're built for that, to be fast and efficient at doing that.
Yes,
the Tesla takes a kilowatt just to stand still running the GPU. That's going to go away.
Right. Okay. Somebody on our live stream is asking about ESP8266 and ESP32.
Mm-hmm.
Not my field. What are those things?
Yeah, so those are different targets. So we haven't gotten them.
Those are microcontrollers.
Exactly, yeah.
Okay. But so I'm seeing various vendors listed here, but the ARM, that thing, that's not a microcontroller, is it? ARM Cortex, that's an actual processor.
Well, you can use variety, so the low-level ones don't use these, these are like 50-cent processors,
Yeah.
They're not $10, or...
Okay, fine. All right, let's take a look here.
Yeah, so here we dig down into more detail. You can...
Yeah.
Open those. Okay. So
there are lots of hoverboards.
Sure. This is just an example, Stephen.
Okay. Yeah, okay.
So what we're showing here is that, there's that microcontroller on the left, and that's doing a very specific task. And so we can generate an embed code.
Yep, I get it.
Okay. Now, on the academic lab side, what's happened there is that there is sort of a wholesale replacement going on on these expensive boards from National Instruments and other places to these micro boards. And that's happening both at the high school level where you have maker labs, and it's happening at the university level. This is obviously
a Batmobile.
Well, sure.
Okay.
Okay, next
All right,
slide.
I get it.
So this, I'm sure you've seen the V diagram before in systems development.
Well, actually, I haven't, but
so this is how you develop an airplane or a rocket or something like that. It's typically following this development model. Do you know what I'm saying? So it's getting very, very concrete there at the bottom.
Yeah, okay, fair enough. Fine. Yeah, I understand this. By the way, on the live stream, asking why are these ESP things so different?
Yeah, because the instruction set is different. So
okay, so that's a specific reason why. I mean, we just haven't created something that we're going to get to instruction sets. So let's get to that.
We're coming there. Yeah, we're getting there.
Okay. Okay, generate the code, compile it, download it. Yep, I get that. Especially with the dude with the sunglasses.
That's right.
What's that?
Sure.
Okay.
So.
Okay. Real-time code execution. Yes, I understand. And I suppose you're going to talk about analysis of code to make sure you hit certain targets.
Yeah, it will return a data object where you can see some metrics. Yes.
I see. So it can say guaranteed to get this executed by a certain amount of time. Okay.
Don't run it because you're going to...
I can't run it. Yeah. Okay. Okay. So this is an outline of what's supposed to happen. So this is
so so you know where it's used and by different groups how it sort of fits into them. What is it that we provide then? You know, so we take basically these systems objects that we have built for control and signal processing. We can take those, and if you have one of those objects, we automate everything from there on out, if you see what I'm saying.
Yeah, I get it. I get it. I mean, I would have called this function microcontroller embed code because it's in the embed code family and it's about microcontrollers. But yeah, I mean, that's a detail.
Okay.
Right?
Yeah, it's based on the function embed code. So the design is also...
I'm aware. Yeah, right. So I would just name it that, but that's details.
Okay.
Okay, so now here, what you're saying is this is the embed target. Yeah. I don't quite know what this is.
That's the port, that's the mechanism through which it goes to the target.
Okay.
So the first argument is what goes, the second argument is the details of where it goes, and the third is how it gets there. That's the intermediate.
Right, but so this is a parameter, basically, of the Arduino Uno. This is a parameter.
Yeah, and so the second this we can get to the design in the ref page. So the second argument has three sub-arguments. The first is the name of the target. The second is what are the input pins or ports. And this one has none. And the third is the output. And
okay. I strongly think that should be an association. If you're going to do it that way.
It could be.
Right. I even think that the whole of this ball of wax could be an association, because I think that I could imagine all kinds of funky things where this is, for example, Wi-Fi connected rather than a dev anything.
You're absolutely right. The third argument is an association, and this is just a syntactic sugar.
Okay.
The second argument is also a list. Yeah, we'll get to that. Yeah, it's something close to what you have in mind. Yeah.
Okay, terrific. Okay, so let's keep going here. So this is, I mean, this state space model thing. So
the models here are kind of close to trivial. Do you know what I'm saying?
Yeah, I understand. I mean, but my question is, well, what you're going to get to is what kind of code can live there.
Yes, it's very limited, but that's also exactly, that's what they are limited.
Okay.
That's what I'm saying. But there's no need particularly for anything very general.
For goodness sake, with a clock frequency, give it in units, 16 megahertz, please.
Okay. All right. Okay.
We have units, let's use them. We might consider using units for the size, source code size, 1439 bytes, possibly. Not sure about that. Less certain about that. Okay, let's take a look at this.
So this shows both the code generation and also the device framework working in tandem.
Okay, so let's take a look at this. So what you're showing here is there's a filter.
Now we sample that to discrete time is sampling a continuous filter to make it a sampled system.
I don't really understand. Well, okay, we're going to get to that. These various control system models, basically, how they relate to just arbitrary code, and how they relate to things like interpolating functions and things like that.
Yeah. So yeah, you can. Yeah, when we get to the design, you can see that object will also give you the source code, and then you can see the corresponding code for that. For those objects.
All right, fine. Okay, so let's take a look here. Okay, open a serial connection. Yowie, kadowie, what the heck is all this stuff?
Yeah, so we are setting up an input, and so this is something Roger and I discussed. We need to actually get a higher level function, so we are not doing so many functions to read and write using the device framework.
Yeah, it seems kind of crazy. So, I mean, you've got a serial port.
So we have an idea for that, for how to streamline that, but it's not there when this isn't.
Okay, so hold on. Let's just think about this for a second. So what is actually going on here? So you're trying to...
Okay, to understand, you have to look at what was embedded above. So if you look at embed microcontroller code above, it tells what the inputs and outputs are. So the one input is coming to serial and the other one is going out.
Okay, fine. So that's what's happening in the microcontroller. And this is actually testing the microcontroller from...
Exactly.
Yeah.
Okay, fine. So this is seeing whether it actually does what it says it was supposed to do.
Yeah.
Okay, so this is rather grotesquely, I mean, ultimately what you're doing here
is we are reading the input and then sending the next. We are reading the input, the output of them from the Arduino.
Yeah, I understand. So you're doing a cycle where it's read write, etc.
Yeah.
So it's almost like a continuous task. I mean, in the case where, I mean, you could as well be thinking of this maybe. I mean, I don't know how it ends. How does this end? How does it know how many? Is that SP thing the thing that?
That's the scheduled task. With it's executing. Then finally we stop the task.
Oh, I see. This is it. So you're actually. So this is in fact a continuous task.
Yeah.
Except that you're using a scheduled task to do a continuous task because we don't have continuous task at this time. Right? It's scheduled based on the sampling of that microcontroller. Because we sampled it at that rate. Oh, I see. Okay. All right, fine. So device read time series would be another thing that is essentially reading. So what you want is device read write time series or something. Yeah, yeah. Is that roughly what the functionality you're talking about? Yes. I forget the name we said. I discussed this with Igor at some point. Yeah, well, tentatively, just for the sake of me understanding it. It's that. It's device read, time series, read write. Wow. So was that exactly the function you guys invented? Yes, with a different name, and we also have a design spec for that. It's just not implemented. Okay, fine. All right, let's keep going. What the heck is this? Okay. Yeah, it just shows how it's related to the other projects. Okay. What I want to know, though, is how does this relate to Arduino Link? Yeah. So Arduino Link is part of the device framework. So. And why am I not finding it? That's just the craziest thing. Okay, all right, fine. Okay.
So in this framework, we are opening a connection and then reading or writing, configuring it, and so on, right? And there is a connection back to the Wolfram session.
Okay, so this here, but this has some ability to send code, correct?
Yeah, it sends code, yes.
So how does that relate? Well, I guess I'm going to see the design that you're proposing for sending code, because we actually want to have some external code representation, and we've had several projects working on that. And I think, for example, the new compiler representation with type specifications is a much better way to do this.
Possibly, but it's sort of, I don't think it's going to land on them, because when are they ever going to want to do 8-bit processors? It's just not going to be in this.
Well, maybe so, but I think syntactically we want to use those same structures. Well, anyway.
I understand.
Okay, all right.
It may make sense because that one is isolated to the first argument. So any Wolfram language code that comes in the first argument of Embed Microcontroller code, if that can be handled by the compiler, we can get an equivalent C++ representation that we can take and cross-compile onto this.
All right, fine. Okay, so now what do you go to? Okay, let's go to the guide page here. Oops.
You need Xkernel for that.
Do I need Xkernel? And unfortunately, my Xkernel, some Xkernel version was not working properly here.
This doesn't need to be super fresh if you have a...
No, it just was not starting. So I'm going to need Xkernel, or I'm just going to need the latest DocuTools?
No, Xkernel.
It's built.
Why? Oh, it's built, so I could actually look at it.
Yeah.
Okay. So what am I looking for?
Just open the help viewer, and then you can
okay.
Yeah,
okay.
and type a microcontroller code or embed microcontroller code.
Except that it's barely microcontroller code like that. Is that right?
Yeah, it's in.
I don't trust any search up there. Do guide /
Okay, what do you want me to do? Guide?
Whatever is under that link. Suba, do you remember?
It's Microcontroller Kit guide.
Okay, I see it. This is barely echoing my keystrokes because I guess it's being developed. Actively developed. So guide / microcontroller kit, unless I misspelled that, is not being found.
No, it's microcontroller kit / guide / microcontroller kit. There's a microcontroller kit up front also.
You're right. Okay, there we go.
Now, the third thing that here that's called workflows, they're really projects, like little projects that you can do. It's worth looking at. I don't think it should be called workflows.
No, it absolutely cannot possibly be called workflows. Is that a function name? Is that a proposed function name?
No.
Okay,
No.
so fine. Oh,
No.
okay. It's just a link there.
So click on one of these, and you can see sort of the
There's nice documentation.
yeah. And so there's typically like parts and how you build it, and then the various steps.
Okay, well, let me look through this. Great.
It'll leads an user step by step to replicate this. So it's useful if somebody wants to do it.
Right. So, I mean, does this match the workflow documentation style?
Yeah, that's a little, So there are little rough edges because we.
Well, it might want to be some different style of workflow. If you think it's a different thing, I mean, if either you've got to match the workflow documentation style, or you've got to decide it's your own thing. It's a kind of a maker workflow or something. I suspect it will be better to match the workflow documentation style.
Okay. Because in the workflow, there is no that big introduction. Some of the things we can change, but there is that not big introduction.
It's useful to have that introduction.
Yeah.
So you might want to call this something different. You might want to call it something like Microcontroller Workflow, or I don't know what it should be.
We have similar things for the Unity Link, you know, like little projects that you can do.
Yeah.
You know, that you can follow step by step.
I don't know whether these are, you're saying these are more projects than they are kind of, you'll want to do this often type workflows. In other words,
yes. I think that they're kind of like, they're step-by-step projects. It's projects, here's how you do it yourself.
Sample project or something.
Right. Yeah, sample project is not a bad, but that's what they are.
Fine. Then that's what we should consider using.
Well, look at a few of them, Stephen. I think
okay.
And some of them are a little bit more elaborate because there are more parts that you need to get.
Okay, so this is the one where you have that whole big crazy.
We hope to streamline, yeah.
Okay, let's go back up here. Drive a robot along a path. Okay. A beautiful zone Spikey.
Yeah.
Aren't we lucky that our rhombic hexagonahedron can be zone constructed?
Right.
Okay.
This one has the DC motor. I know has more parts. This one
this has. Oh yeah, this one also has.
Yeah, a few parts.
Okay, don't forget the batteries. What?
Yeah, we are exhaustive. So
should be stacked upside down on it. Weird. Okay, so this is definitely a sample project. This is hardly a part of a grand workflow that people are going to need when they build, landers for Saturn's moons or something.
That's right.
Okay, it's a bit grotesque. What's all this doing?
yeah, this is just assembling, getting the libraries.
That's really quite weird. Okay. What is, viewed in terms of ordinary code. So if I want to have a microcontroller where it receives, are they they're getting digital inputs, yes?
So the way that this is typically done is that you write C code that does every step of the thing. Read this, do that. But there's no design. You don't design using that. You just do the actual code. Make the microprocessor.
I understand, but it's got A to D on the input. So
yeah. So the microcontrollers usually have A to D, D to A converters built in.
Okay.
They have analog inputs actually.
Okay, fine. So naively, I could have a function, a microcontroller that just, squares a number or something.
Yeah.
Yes.
So what would happen is voltage of 2 volts would come in and 4 volts would come out.
Yeah. Yes.
Okay. So in our representation, we're using state space models and things like that to represent what's actually going on inside the microcontroller.
To get a limited world, a more, we might want to build that out, but I think that we don't know how much to invest in this area yet.
Yeah.
And we think this is the most important case.
But so
this is where you want to run on the metal.
Yeah, I understand. But if we were to use the compiler, for example, we certainly know what functions are being used because we know if they're in the RTL, we know where they are, et cetera, et cetera, et cetera. We know what's involved. Mm-hmm. Right?
I think that there could be a future version where we do use sort of more of a compiler infrastructure, but we can get a year's worth of interesting feedback and use by providing this and learning more about sort of the essence of use cases.
Okay. What is a state space model? Sort of mathematically, what is that?
It is when you have a system of first order differential equations or first order difference equations. Mm-hmm. So the only thing you need to do is to, let's take the discrete case. But a system of first order difference equation. It just means that x1 at time step k plus 1 equals a function of the state at time
okay,
k.
Fine.
And That's what it is.
So essentially what you're saying is the microcontroller is going to execute, it's going to step through these differential equations based on that are receiving.
So it needs to be discrete, it needs to be difference equations. So even if you model it using differential equation, you are responsible for discretizing it and making it difference equations.
So state space model, then you say, is
state space exists for both for differential equations and difference equations. The ones that the microcontroller ultimately wants is difference equations, because it needs to do things step by step, you know.
Okay, I'm back. All right, let's look at state space model.
So Stephen, let me say, so if you want to really see what the state space model in terms of code, I think you just look at that first workflow, the first project, or even the DC motor. And if you look at the source code, you'll see the equivalent C code representation for that. So, yeah, the first one, for example. And then if, the discretize and deploy the filter. And then go down and just copy that microcontroller code data object. And if you do needs microcontroller kit and ask for the source code, it will show you what was that equivalent source code for that discretized transfer function model. But first you've got to do needs microcontroller. And then ask for source code property. Yes. Yeah, and you see update TFM, that little down, there's an update. Yes, so that is the,
my gosh, what is all this junk here?
yeah, so that's setting up, getting the serial data and so on. That's an interrupt routine that's receiving the data. Yeah, so this is all that we automate for the user. So,
right, but this is the actual model up here.
Yeah, that update TFM, that's what is getting updated at. The TFM.
So, when I do this here, can I see the 0.02 whatever, or is that?
Yeah, it should be there somewhere. Yeah.
I mean, this has been somehow munged.
Yeah, it's been munged, because if you do a transfer function expand on that, probably that's what you can see.
Okay, I understand.
Because we see the denominator there, but the numerator has gotten expanded.
Okay, fine. All right, so let's go back here. What were we looking at? Okay, so the
guide page might be.
Guide page for what?
Good overview. Oh no, I like wherever you want to go, Stephen. Okay.
No, not there. The guide page for
this. If you back out of that project file, you come back to the guide page. There.
Okay. So now. Okay, so we've got these various system models, which you tell me are essentially these differential equations that turn into difference equations.
Mm-hmm. Yeah, and that's what when you hear us talking about that in signal processing and control, we say it's a continuous time model. It's a discrete time model. Continuous time means differential equations. Discrete time means difference equations.
Okay, so that's the discretization.
Yes.
Yes.
Okay. And these are, okay, fine. So now what's this?
This is how you wire together these objects.
Oh, okay. Right, so you can, now, what's the relationship between filters and, I mean, a filter is something.
A filter is they're all represented as transfer function models.
Mm-hmm.
So it's using the same sort of system representation. Now, a filter has an input, and it gets transformed to an output. And that's exactly what a control system is too.
Yeah. Yeah, they are all that. They take some inputs, they have some little memory, and they have an output.
But so these filters are operating in frequency domain or what, typically?
No, in the time domain. So Butterworth Filter correspond to a set of, continuous time, it's a set of differential equations. Discrete time, it's a set of difference equations.
Okay.
Tells you what it does to the signal.
Okay. And if I look at those random things that you had in the first page, and I look at the code that they have in them, I mean, like I don't know, the flight controller for a drone, is it representable in terms of these things?
Yes. So,
and how complicated is it typically?
It depends on what Stephen means by that, Suba. But give your answer, Suba.
Yeah. So typically, at the very low level, those controllers are obtained by putting together these different models.
Mm-hmm.
Yeah, but they'll also have a slightly advanced thing where they have finite state machines, which we don't have yet. But these are what comprise those controllers or filters. These are these basic systems models.
Okay. But I mean, so, if I were to look at the code, how long is the code typically?
So for a Butterworth filter, it's a few kilobytes. The entire thing, getting the...
No, I understand, but what about for something like, a drone, a hoverboard, something like that? What are the sizes of code, and how many weird exceptions do they have in them, and how much of it is just, how do you... I just don't know what code looks like. I mean, in the case of, standard kinds of code...
So the core still looks very much like what you looked at.
Mm-hmm.
Okay. What can happen, in particular for flight, because it's a fairly nonlinear process, is that you have many of those. So under these conditions, we use this simple model. Under these other conditions, we use this other. So for even the Boeing, has that. A Boeing passenger jet is in fact that for the core flight control. Everything is a little bit more complex, but let's say they have 30 of those models that run for different parts of the envelope.
Is that typical? Is that a typical actual number?
That's an actual number that I knew from some while ago.
Mm-hmm.
It's not from now, but from my previous life.
Mm-hmm. Do you think it's now a lot bigger than that, or do you think it's complicated?
I think it's grown in a variety of ways. Boeing had you take into account more information.
Mm-hmm.
So the what's called the order of the model, the number of states in that difference equation is higher.
Okay.
So they model more details.
But so I mean, a typical thing would be, if the plane is within, I don't know, if the plane is at 38,000 feet, and
it's a certain. So the envelope is typically parameterized by speed and height.
Mm-hmm.
And you can use more elaborate sort of.
And what about on a plane? I mean, if it puts its flaps down and things, does that change? I mean, the configuration of the control surfaces and things, does that change it too?
No, the flight envelope are just these parameters, like angle of attack, velocity, the height, and so on.
Okay.
Yeah, and then there are hard limits on how far the control surfaces can go.
Yeah, but then but so the flight controller is controlling. Ultimately, it's controlling. I see. It's controlling the control surfaces. Then, like it's flipping the ailerons up and down. Okay.
Yes.
I see. I get it. But I mean, it's presumably it matters whether the wheels are down or not, and things like that, which is not something the flight controller is going to figure out. I mean, it's not going to do that. It's somebody else is going to put the wheels down, presumably. Maybe not anymore.
Right, but that might mean that that's what I'm saying is there might be more parameters to determine how many of these models, because dynamics changed when the wheels are down.
Fair enough. Okay, fine. But so the organization. So I mean, with the stuff that we're describing here, somebody would write. I mean, what does the if look like to say if the plane is in transonic flight, then do whatever? What does the if look like in this system? Is that what
we're not doing that particularly? We can do some if, but not the case that you describe, where we really kind of effectively have, like in the case we described, like 30 of these state space models that are tied together in a state machine. From this, you go to here, to here, to here.
Okay.
Depending on conditions.
So we can't do that.
We can't do that very easily.
Yeah, but what limits us is we don't have a model representation to hold that description.
we can do that in the future. I'm just saying that this is
okay, fine. So we're dealing with a single one of those, conditions.
Right.
A state space model for a single one of those conditions. We're not dealing with a transition from one condition to another.
That's right.
So it's as if, if these things were interpolating functions, or neural nets for that matter, with neural nets, I don't think we've had that issue particularly yet. For example, you could well imagine something where it says, okay, initially run a classifier that says whether it's an aerial photograph or a microscope image.
Sure.
And based on that, just, use this object recognizer rather than that one.
Right.
I don't think we've quite set that up yet.
Right.
Yes. So once we have that description, we're able to describe this in the Wolfram language. It'll be useful for this functionality too. And we can
there's no barrier per se, Stephen, but it's better that we have it as a high level description in the language, because then we can actually design it, manipulate it, and do things.
Sure. Okay. Microcontroller targets. So what is this? So this is for a way for the user to know what we support. Okay. So this is where the question that we had about ESP things would be a future thing to support or something. Is that right?
Exactly. Yeah.
But everybody here is using C code and there's using some kind of compiler.
So the vendor of the microcontroller does provide a compiler. Mm-hmm. Because otherwise it's a very hard to use product. So they need to get that,
So we have extensive tutorials where we go step by step how to set it up and so on.
Okay, so wait a minute. In the modern world of external evaluate, there's this notion of system install, which is like if you want to install a Python system or something, there's a system install of the Python system, so you get version whatever it is.
We haven't done that, but that would be nice if we can get that set up.
Okay, so that you could plug into the system install mechanism.
Possibly. I just don't know whether that requires legal agreement with the different vendors to be able to do that. And there's a lot of things.
Yeah, I understand. I would suspect that, no, I think you're just taking, it might come from their website or whatever else, but we're just packaging it so that you just use this one function and it will install what you need.
Yeah, but we've had problems in other places where they sort of change where it does. You're not allowed to do that because the user needs to be provided,
Yeah, right. Yeah, right. I understand. Where there's a click-through license, for example. Okay. So, although we do have a mechanism for dealing with that, I believe we have that. For example, for our service connections, we have that. Mm-hmm. Okay. So, I'm trying to understand. So, the C code that gets generated that you were showing me, there is never a symbolic representation of that anywhere. It's not like this case where we have some kind of custom symbolic representation of the C code that we're downloading to the microcontroller. Is that right?
Yeah. Yeah, that is not part of it, although we can inject it with external libraries.
No, but I'm asking the question.
Are you using Symbolic C or not?
Under the hood, it's using, so when you load Microcontroller Kit, it loads Symbolic C, and that's how we generate the C code.
So it is using that, Stephen, at some point there.
Internally, that's what is being done. Symbolic C is generating the C code.
For these microcontrollers, there is another thing. So you want to marshal the compilation, and then actually getting the compiled code on there is its own little thing. The loader for these things is not what you think of as sort of in a computer with an operating system. Stephen?
Yeah, just 1 second. Sorry, back up. Could you say that again?
So let's say that you've compiled it. Then you need to get the code actually on the microcontroller somehow.
Yeah, I get that. Right, okay. That's what this is doing. That's what this device configure thing is doing. It's doing an upload, right, of that code to the microcontroller.
Yes, but yeah, it's doing it through a serial connection.
I understand. But how else are you doing? How are you doing it?
Yeah, so we are yeah. So this one is opening a connection to the device and maintaining.
I see it, right. But maintaining a connection to the device, yes.
But we are not. We are giving it to the third-party toolchain. If you look at that original diagram, it's just a one-time deployment. That workflow that where it was in the first slide.
Slideshow.
First slideshow.
The first slide.
In the slideshow, it's where is?
Where in the slide?
Yeah. Just keep going. Yeah, this one. You see, after we generate the source code, then we give it to the third-party toolchain, and it's just a one-time deployment.
Can I see that from the embed code output? How would that work?
No, that's happening behind the scenes. It's doing a run process. It's calling those things and deploying.
But how does, I mean, look, physically, the microcontroller has to be connected to your computer somehow, or you can't send squat to it.
Yeah, yes. So that's the other difference between this one and Arduino Link. So you can do that workflow that exists in Arduino Link, because we can connect to an Arduino, because an Arduino has two things. It has a bootloader on the chip, and it also has a USB to serial converter. Not every microcontroller, if you just have a bare metal microcontroller, it doesn't have that. So,
okay.
So we have what's called a hardware. So in the general case, we have what's called the hardware programmer. Again, it's in that workflow, that diagram.
No, I understand, but I want to see it in the case that you've. Okay, so you have here one of these. Let's try one of these things here. Okay, so embed the code.
Yeah.
So in this case, microcontroller code data is some symbolic representation of the embeddable code. Is that correct?
Yeah, so it has two things. So it shows that it first generated the code. That's the two LETs that we're trying to show. And then it also says that it has been deployed.
How does it deploy it? So when you say needs microcontroller, how do I tell it that I have some weird little thing connected with wires here?
Exactly. That's the third argument of embed microcontroller code. So in the Arduino, because if when you say Arduino,
I see. I get it. So that is basically whatever the configuration thing is, it's putting it out on that dev.tty.
Exactly. So if it's an Arduino Uno, you just have to say that, and the others are we automatically.
What does that look like when it's an IP address in a Wi-Fi system?
Yeah, you can look at Embed Microcontroller Code, and in the details section, we show that different keys of that association. So the third argument, as I said, was actually an association. So if you look at Embed Microcontroller Code, and in the details section, this is getting into the design of this. Yeah, if you go down, this is the third argument. Yeah, so the programming, we can say, what is the connection port? What is the programmer we're using? Where is the...
What is a programmer? What does that mean? That's a tool chain?
Yeah, that's actually, the programmer is actually a hardware device. The programmer is actually a software. The external programmer is the hardware, and programmer is the software.
Okay. So that's the name.
Yeah, that's what they're called, the programmers. Yeah, they communicate through certain pins on the microcontroller to put it into different locations in the microcontroller.
Boy, this is a complicated setup. It's cool. I mean, the thing I'm trying to understand is.
Okay, there's also a tutorial which shows that in detail.
Okay, I get it, but I'm trying to understand in So this is a much more raw thing that relies on the fact that an Arduino has a certain communication connectivity mechanism built into it.
Exactly, yeah. So that's why you're able to say device open like that. Not every microcontroller you can device open from a...
Yeah, right, because it doesn't have any way of communicating with the world.
Exactly, yeah.
Only this programmer thing can communicate with it, right?
Yeah, yeah.
Why please spell out configuration? You've got so many big words here, you can spell out configuration.
Okay.
Okay. Whew, okay. Fine. So let me ask a few other bizarre questions. Okay. Like if somebody wanted to use this in a very lightweight way, does it make any sense to use it in the cloud? I understand that you can't connect. Let's say you used it in the cloud, you use this as and then you download to your computer something which is some kind of package that you then feed to your programmer thing, and it then does the programming. I mean, I'm just trying to understand if we wanted to provide this, for example, to manufacturers of microcontrollers, and we said, here's this cloud-based, design space, where in the end of it, you just press a button and it splurts out a file, a dot something or other file, and then that's what you just load somehow into your microcontroller programmer. Does that make any sense?
Yeah, because the Arduino already has that, where they can download from the cloud right to the Arduino. We just don't connect the cloud to the because even our device framework doesn't go from the cloud through the actual physical port. That's why we've held off. But that's possible.
Okay, that's interesting. So hold on. Let me try to understand what you just said. So I mean, in general, downloading, the cloud to reach an IoT device, for example, one of the main problems is what is the address of that IoT device and how do you open firewalls and things to the point where the cloud can squirt something out and have it end up in the IoT device?
Yeah.
Right?
Yeah.
And that remains a stupid unsolved problem of the IoT world, is how that authentication works.
Yes. But just talking about the Arduino, it's we should be able to go from the cloud because the cloud doesn't talk to the actual ports on this machine. But we should be able to just say in the cloud that, I'm running it on this machine.
Yes.
And download it.
So wait a minute, what do I download? It's some kind of bundle of stuff that then goes to the programmer that What is it? It's
because the cloud should have this third-party tool chain. It should have the programmer also. Yeah.
And is that doable? I don't know.
It is, because Arduino already has that. Because they have the...
No, but that's a complicated licensing story, right? Because
No, this is all complicated licensing if you want to do that.
Right. I mean, but not for us, but for a vendor of microcontrollers, they could do this. If they had a private cloud instance of our cloud, they could do this. They could host such a thing. Correct?
Yes.
It's interesting. And are there comparable things out there other than for the Arduino?
Yes. I think TI also has it.
Okay.
For the Arduino, it's the Arduino web editor.
Okay. And are those web editors for like Arduino C, or are they for things like, here's a Butterworth filter?
For that, that's what we provide. So if you go in the Arduino world, then they have to manually get the equivalent code for the Butterworth filter.
Okay, so fine. So I mean, what we could provide is something. Yeah. Right. What we could provide is something where you go from a notebook in our cloud or in a private instance of our cloud to the actual bundle of stuff that needs to be downloaded to the microcontroller. But the last step there requires going through the programmer software of the microcontroller vendor.
Yeah.
Is that right?
Yes.
That's interesting. So, okay. So then, and when people program Okay, fair enough. And I mean, one of the nice things here, obviously, is that one can have notebooks that basically specify a bunch of, like your sample projects here, that specify a bunch of code, and that if they were configured correctly, it could just be, there's a notebook in the cloud, it just talks about Butterworth filters. At the end, it just has some function that just says, okay, give me the file, run it through the programmer thing and give me the file. And that's essentially your microcontroller embed code thing, right? Because the current embed code function does not do what you are doing here. The current embed code function, right, gives you a thing that you essentially copy paste to whatever environment you're using. It doesn't do, it could use PubSub, for example, to actually inject the code or whatever. Do you get what I'm saying?
So, okay, we are using the programmer to inject the code into the microcontroller.
I understand what you're saying. I'm saying that, and you're specifying a port to do that on, right?
Yes, yeah.
I'm saying there are two steps. So embed code, right? The normal embed code, not your embed code, but the normal embed code in the system does not do that. Right? You know what the normal embed code is.
Okay. I get what you're saying. So that's exactly what we're showing with 2 steps here, because even embed microcontroller code is a 2-step process. It generates the code. I get what you, and then we can take that code and then, we can just generate that code, hold it, and then invoke something later and deploy it.
Right. Which is what you're doing with the microcontroller code data thing. Is that correct?
Yeah. So this one just combines both those steps into one. Yeah.
Right. But what I'm arguing is, so the point that I'm making, your microcontroller code data thing is, okay, in the case of ordinary embed code, right, for JavaScript, for example, you actually get a lump of JavaScript code that you can see in the notebook that you copy paste.
Yeah.
Right?
Yeah.
Okay. Now, we have not done the connection. We looked at doing these connections into IDEs and things, where instead of using copy-paste to transport that code, you use some other kind of mechanism, right?
Yeah. Because in our case, it would just be using that code data, getting the source code, and then linking it, however, to the IDE. Because that code data gives the source code. So
sorry, I spaced out for a second. Hold on one second.
So the embed code gives, say, for example, the other languages code, which we can use in the IDE, right?
Yep.
So here also, from that microcontroller code data, we can get the source code.
Which you showed me, which was cool. So that's the C code, which you could, in principle, just copy paste and stick into some kind of programmer thing.
Yeah. So if it's a microchip thing, you could stick it in there and then compile it from there.
Right.
So and you could manually do those last steps. And sometimes you do because you want to tweak, you want to add something to it.
No, I understand. We might want that but then the workflow that you were imagining is when you feed that C code to the programmer. I find these names very confusing.
Yes, they are confusing.
Is there a more decorated version of the word programmer? So that it doesn't remind me of everybody who,
human.
Yeah, right. Well, anyway, who knows? Is there a more decorated name?
Yeah. So no, this is the one this is I think maybe the only one I've come across.
Okay, fine. All right. So let's say we'll call it the microcontroller programmer. Let's say that you are okay, but what you're telling me is the output of the microcontroller programmer is what? A blob of binary stuff?
Yeah, it's a binary. So the program, it goes through several stages. So it has some binary stuff and also the address where it should go in the microcontroller and so on. And then the programmer takes it and puts it at those addresses.
At the very low level. The very first computer that I used.
Yeah, this is very low level when you get down to it. Yeah.
Okay. This is very close to that, Stephen, and because it effectively has, it's bare metal.
Yeah, right. I know. I understand. It's not a relocatable binary. It's at a fixed address, et cetera, et cetera, et cetera.
Yeah.
And by the way, you have said that because you have a clock frequency there, you can say for the microcontroller code data, you can say what the execution time is and things like that. Is that correct?
Yeah, that's the sampling period in the model.
Okay.
So we say what is the rate at which we want this to execute.
I understand, but by the way, if
they may or may not succeed, right? You might have overtaxed what that particular hardware can deliver.
But can we simulate that? Can we tell you?
Yeah, that we can. Yeah, so the only way to find out is if the microcontroller acts weirdly. Because there's no way to, because it has to do a certain number of instructions within that time period, right? How do we know that whether it has, when it was really implemented? Because there is code that we can actually simulate, but yeah, but that will be too much work for us.
Yeah. Okay. Fair enough. Okay. All right. So I'm trying to understand. So the thing that you are saying we could do is we could have something, in the cloud, notebook-based kind of design that then could be connected to the microcontroller programmer of some particular vendor's microcontroller. Then the result is you press a button and out comes this binary file, which, you can like download from your web browser. And then somehow you have to get that binary file into the microcontroller and you could potentially do that because microcontroller is connected to dev TTY, blah, blah, blah on your computer.
It might be better to get the C code version of it.
Okay.
Because there's some dependence there because they have different headers and other things, but nevertheless, it's fairly neutral. And those environments where you edit C code, they're usually integrated. So the programmer is sort of part of that.
So it's like the IDE situation that I referred to earlier. If those IDEs have APIs of some kind, or have some pub/sub mechanism, then you can potentially, auto-inject the code into the IDE.
That, or you can follow the copy-paste model that you described.
Yeah, I know, which seems to work fine.
What we supply here is a more automated tool chain.
Yeah, I understand. If you happen to, you're right. But I'm saying I think you should break it apart or allow it to be broken apart.
Yeah, the hooks exist. So it's just the question of, if we can work these out with those vendors and then we can inject into their IDEs.
Right.
Well, I mean, that's what I said. We don't necessarily need to inject it into the IDE. We can do that too.
But you can do a copy paste. That's a, this is automating so much stuff you can survive with one copy paste.
Right.
Well, this is very cool. So there's presumably some detailed design stuff here. Roger, you've probably gone over it.
I've gone over it. I mean, you will have opinions, but I also want to make clear for us, I think it's important that we limit, how far we go until we sort of get feedback from what people really want.
What is this external type signature thing?
Yeah, so these are some things that, because this one needs the type 2, just like all these other things. So what is the name we should call it? Because Embed Code calls it external type signature. I've seen a bunch of names around. There is audio type. Here in our Arduino Link, it's return type. Then there's even data type in the system. There are all kinds of type names.
Well, clearly in the compiler, it's the typed. Typed is the general wrapper.
Yeah, it's but it's a wrapper, right?
Yeah, I understand. But what you want is, what is this a type for?
It's for what the data type is, whether it's an int or unsigned 8-bit int and so on.
The data type for what? That's expected to be in the C code, that the C code is expecting.
Yeah, the variables
in the depend on the A to D converters and things like that of the microcontroller.
No, so those inputs and outputs of the system model, what we want them to be.
No, I understand that, but when it's running on the microcontroller, the input is coming from some port that, some wire, some pin that has presumably an A to D converter.
A to D, yeah, and that is usually it can go up to 1024 or something. It's some value like that.
Okay.
Maybe we would like to convert it into a raw value like 5 volts or 3.3 volts, or maybe we like to store it as an int. Just store it as an int as.
Okay, so the question is, when the input comes in, I mean, I'm sure these microcontrollers have endless options for how that works, and endless different ways that the A to D.
So, Stephen, can I make you look at a few more? I assume that we would get back to this. Okay.
Okay. All right.
So when you're back for your trip, but can I ask you to just click on that web page mock-up down there, in that the document for the.
It's all the way at the bottom. Oh yeah, that one. Sorry.
This is a mock-up. Click on the magnify so you see it. So, first of all, a couple of things. We've demoed this at various trade shows. We have a beta test running right now, about a dozen beta testers.
Okay.
And we want to open up partnerships, and we have some contacts, but we got to have something to show them, which we have now. And so clearly there's joint interest. It's interest from us, the interest from the microcontroller makers and the microboard makers.
Yeah, I should probably, I do know some people in this space. You should
right
talk about that in a separate discussion.
Absolutely.
Actually, I know several people who might be super interested in this.
Good. But I'm figuring, I'm glad that we covered what we were able to cover so far, but clearly I know, we need to go back to this one more, so.
Yeah, but I think this is fine to get, I mean, if this is presented as a thing in development, I don't see why we shouldn't have this page out there, where it says it's a beta version or whatever else it wants to say. Preview or something like this. Probably preview is the better term because, there are things we're going to want to change. But I understand. I do think it's worth explaining the workflow of going through the cloud because I think that's a really interesting workflow. I
don't really want to add in the cloud at this point because that's another...
Well, fair enough, but partnerships should certainly understand that.
Yeah.
Yeah, interesting. I mean, but why don't you show in this case here? Yeah, you've got to be able to show where that comes from. I mean, because that's what's really exciting, is that isn't, that just looks like, I don't know what the heck that looks like there. But what you've got to show is that you can compute. The first example should show how you actually go from the Butterworth filter to the thing that, or whatever you want to call, have in there, to something which is, a kind of, what can I say, is a sort of, scientifically motivated thing or something, to something which automatically generates the code, etc. Right?
Are you talking about that image just there?
Yeah, I'm talking about this example. I'm saying your first example should have something which makes it clearer, and I would suggest having call-outs in it that basically say...
So bring another example, because this example is super simple. So I'm saying this is like hello world.
Right, but I'm suggesting that you have an example, even in the simplest case, you have an example where this thing here actually visibly has something which you can, I mean, even if you just wrote that out, a state space model of blah, 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 or whatever it is.
Oh, I see.
It would still help, because otherwise I don't know what the heck that is.
That's true.
That's true. Jeremy has suggested that. Yeah, that was, yeah, okay.
It was, it just looks like an extraterrestrial spacecraft that landed there, and you can't tell where it came from.
That's true. I get it. So you had a much simpler point than I thought.
Right. Yeah, I mean, this is very interesting. It's nice. You should have shown me this page first, probably. Maybe I wouldn't have understood it.
Well, I think that taking the journey that we did was good. There's many other ways we could have done it, but it was.
No, I think I understand what the story is here. I think I can even point you to some interesting partnership connections. This is great.
The other side is that there are millions of users of this, first of all. But all of these microcontroller makers and microboard vendors have also communities that we can directly reach, which is good.
Yeah, sure. But I mean, I assume that some of those companies are also trying to work on, neural net deployment things. And, since we have a tool chain that involves, where we can generate like neural net stuff, that's, I would assume that some neural net...
As you start stepping up, from 8-bit to 32-bit and other things, then it becomes realistic to deploy a little bit more
Well, except
complicated.
that those guys are actually moving down to smaller bit counts.
Right. But I doubt that they're going to move below 32-bit for neural net.
That's not true. It's not true. Absolutely,
Really?
people are. Yeah, absolutely. There was actually a kid at our summer school this year who's trying to get a company started that's based on very small bit count neural net things.
Really?
And in fact,
Wow.
yes, 8-bit and so on. And has a whole bunch of schemes for how to do that.
You alone in your house probably have 100 of these running that you don't even know about.
Yes, I understand that. And I'm about to do this big project. I've just been instrumenting my HVAC system, right? That's what, so I'm going to finally learn control theory because I'm going to experience it, so to speak.
Yeah.
I mean, I don't know whether you saw that the initial data from something had this crazy thing that was switching itself on and off every 5 minutes.
No,
So
I haven't seen it.
there's clearly a bug. So, and I think the actual current control system is totally stupid. So I'm going to see so we have some Raspberry Pis and things, and they're supposedly getting sensor data. I have some Wolfram Language functions that read the sensors and set the actuators. And now all that's needed is to actually put in the control system. So hopefully in a couple of weeks, I'll be in a position to do that. So I can then boil and freeze, under program control. Anyway, all right, good stuff. Well, very nice, great project. And I'll probably be wanting to look at some more details, but this looked really good. Anything else?
So I think, Stephen, we'll set one up in the week you come back, and we'll try to then because then you know all the context, you get a sense of where it is. You're going to need some repetition, but then we can nail the details.
That's fine. And we might want to also talk with partnerships folk at that time.
Yeah, that might be a good idea too.
Okay, sounds good. Okay,
Thank you.
Thanks to folks on the live stream as well. See you later.
Thank you.
Bye.